Okay, good morning, everyone. Can you hear me? Testing. Can you hear me? Okay. There's 9 students today. Um, but nevertheless, it's already 8:35, near to 8:35 now. We should start our classes already. By the way, this recording will be also recorded lah. Okay, so for those who are late, they can view the recording later on. Today we will have 2 sessions. The first session is the lecture. Okay, we will complete our FFT lah. Okay, as you can see from the screen lah. Okay, so if everything is all right, okay, the screen is okay, then we shall start now. And then the second hour, okay, we will talk about the tutorial. Okay, right. So we start right now. I'll start the recording. Okay, we will record this one. Okay, recorder is started. Okay, so let's say duplicate slide. Right. I hope you can see this. Right. One moment. Okay. I cannot see. Let's see if I want to still see this. Okay. Mhm. Mhm. Alright. Sure. Okay. So if you have any question later on, I will check the chat box lah. Okay. If not, you can also speak through your microphone. Okay. Right. Okay. So the other day we have talked about this FFT, right? Okay. FFT is actually it is similar to DFT. Yeah, it's just that the FFT we exploit some of the symmetricity. Okay, we exploit the symmetricity of the DFT and also the periodicity of DFT, and we found that there's a lot of values that can processes that can be duplicated. Okay, without recalculating. Okay, so actually the outputs. Okay, they both calculated xk, right? They both calculated xk. You found that using DFT, the equations, the original equations, you still can find your sk. And FFT, you can also still find your sk. It's the same. So just that FFT is faster. Okay. So on Wednesday, okay, we talk about, okay, so we are able to change from a DFT equations, okay, split into two smaller DFT. Okay, so this is n point DFT equations. Okay, and after you do some calculations, the scientists found that, oh, okay, we can uh, break down n point DFT into two n over two DFT. Okay, so this is a smaller DFT, which they sum up the even index from the sequence, and then the other one is also n over 2 point DFT, where it sum up the odd index, odd entry of the uh, from the original sequence lah. Okay, so the sequence has been split into two, and also the DFT's length is also shortened by half. Okay, and they found that they can add these two together to get their endpoint DFT, right? Okay, So we can add half of this from the even side, and then the other half from the odd side, add them up, then you can get the full length of the DFT, right? So that's the theory here. Okay, and of course the odd DFT, the odd n over 2 DFT, this part here have to multiply with uh, an exponential lah, Wn power of k, all right? Okay, so in this case, so if the n is 2 to power of something, right? So you can continue to break down this n over 2 to be a smaller DFT until 1 point DFT lah. Okay, so you can continue to break it down, okay, until the smaller DFT, so that you can add all these small DFT together, okay, to calculate the larger size of DFT here lah. Okay, so that's the idea here, right? So the basic calculations, the proof lah, okay, so is here lah also, but in this case, it's good that we know how this DFT come about, okay, through this process, but this is to help you to understand the DFT equation, so that when you applied it, then you would know it is useful. It is actually helpful for your understanding how to use the FFT algorithm. Okay, so what is so great about being able to uh, decompose, decompose endpoint DFT into two part of smaller size of uh, DFT, right? So that's the questions. And then there's a multiplication some more. All right, so let's look at the calculations for this part, right? So look at the calculations here. All right, so there's a summations. Okay, then we know there's a addition, complex addition, assuming F1M, this sequence is complex number, and also this is a complex number. All right, so in general, of course, we know in this course, we are assuming our sequence are all real number lah. But what if, because when we design the equations, that we have to take into account that the possibility, all the possibility lah. Okay, so to be safe, this is a complex number. This is of course a complex number. Then we calculate how many steps they need to calculate to complete the calculations, the computation. All right, so the F1K, okay, meaning that this part, it will need n over 2 square complex multiplication to calculate uh, all the answers from this part lah. Okay, so comparing to the previous DFT, right, DFT formula, we observe that each value of k, okay, look at the second line now, to compute all n values of the DFT, okay, so compute all DFT values, okay, the original equations, the original DFT equations, it requires n2 complex multiplications. Okay, so the complex additions is n squared minus n, but for this case, for our easier understanding, we look at the complex multiplication part first. Okay, uh, this one, if you understand how this n square complex multiplication comes around, then actually you can also calculate yourself how many complex addition get inside here. Right, but for complex multiplication, we already see that this is one um, multiplication, okay, and then you have to do this multiplication for n times, right? And then this k also can be iterated from 0 to n minus 1. So the process of getting all the xk, you need to have n multiply n uh, computation steps. Okay, so therefore you see here there's n squared. Right, so once you are able to break down this xk computation, okay, into these two smaller size of DFT, okay, you found that this part you need n squared over 2 complex multiplications. All right, we are talking about multiplication now, okay, because it reflects the same amount of complex addition also. Also, we just look at one processes first, okay, one computation process. Then F2K here, it takes you also n over 2 square, okay, multiplications. Okay, so by by uh, having a over two in this process, all right, this is not no, this is a division by two. So you actually slow down the curve already. Remember, so this is a number of n. This is a number of computation step, right? Okay, so if it is quadratic, so as n increase, then you saturate very fast. It's grow very quickly, okay, to a very high number. Okay, so if you have over two here, then you actually slow down a little bit. You can be actually no, your computation resources, uh, you have some spare lah. Okay, so you can go for a longer for larger n numbers, okay, for to keep the computations that maybe around here don't go over because your computer has a limited RAM, for example, right? Okay, so if you have n square over 2, you have a divided by 2 factor here. Okay, you actually improve the efficiency of the computation, right? Okay, right. So the additional n over 2 complex multiplication, it is for the w, right? So this one also have to multiply in. Okay, so the number of multiplication is n over 2, right? So the total computations for xk, okay, or if you want to calculate all the xk lah, through these equations lah, so you need 2 multiply n over 2 square, okay, because there's 2 here, and also the multiplication of the w, n over 2. Okay, so this is the total complex multiplications. Okay, so it is roughly like this. Okay, so it's grows slower because of these underscore divided by 2, right? So the result has a reduction of the number of multiplication from n square to 2 multiply n over 2 square plus n over 2. So being divided by 2 is already a very great improvement. Okay, so if you are able to do this, to break it down into 2 lah. Okay, so this is a uh, improvement by when you are breaking down it by half. Okay, and what happens if you further break it down into uh, a smaller DFT, right? So this one also uh, continue to break it down. Okay, so if you continue to break down into the smallest DFT size, then you actually further improve this because your n is smaller, right? And then your uh, denominator is getting larger. All right, so you can further speed up reduce the computation steps, reduce the computation steps. By how much? If you continue to decrease it, right? So let's say the n that you choose of this form to the power of mu, right? To the power of mu. Okay, so meaning that the n is divisible by 2. Okay, if you divide it into the smallest n, okay, you keep breaking it down into the smallest n, the decimations can be performed by log over n times, like log 2m times, meaning that if let's say this is 8-point DFT, okay, and then you are able to break it down into a 4-point DFT and another 4-point DFT. If you continue to break it down, how many times you can break it down? You can break it down to 3 times, right? So the decimation, meaning that the breaking down process, the broke down process can be performed log 2n times. Log 2n times means 3. So you can continue to break it down for another 3 times from here, right? So this is the first breakdown, second breakdown, and third breakdown, right? So that's the process now. So therefore, you have seen this a log 2n times. So in general, if this decimation of the data sequence process continues, okay, see, so this one take away first. Where's my mouse? Cannot see it. Okay, so I need to take this here. Okay. All right, so the total number of complex multiplication is reduced to n over 2 log 2n. So uh, there's a so okay, so the complex addition is n log 2n. Okay, but we focus on the complex multiplications, right? So because if you can understand how the number of multiplication there, then you can also calculate the addition now. So we look at this first. It can be reduced down to n over 2 log 2n, the complex multiplication. You see the square is gone, right? So there's no square already. So let's say n equals to 8, okay? So if you put it in here, okay? So this one give you a 3, this one give you a 4, right? So 12, all right? So the complex multiplication is reduced to 12 steps, okay? How it become like this is because uh, you can look at here lah, huh? Right? So it is because of the butterfly structure. Okay, so you see here, there is later I'll explain to you how to create the butterfly structure. And from here, let's look at how many stages of the butterfly structure and how the butterfly structure can reduce the number of stages lah. Okay, so first of all, you have two input. Okay, this is the xn lah, right? So 2xn should give you 2xk lah. Okay, right? So this is the even number entry. This is the odd number entry. Okay, so according to the butterfly uh, decimations of decimations in time, FFT. Okay, so you need to if you have xn now, xn, you have to group the even number here and the odd number here, right? The odd entry and even entry. Okay, so the even entry will do a normal DFT. The odd entry will also do a normal DFT. Okay, but just that after you finish the DFT, you have to multiply with a factor of W n power of k lah. All right, so with this in mind, so this butterfly is also the same. So let's say you only have two, right? You only have two entry. You want to use the FFT decimation in time algorithm. Okay, so the even number um, will become a plus wn. Let me see. Okay, so you have a line here coming to this dot. Okay, this is the a, and then you have another line here pass by this factor wn, because why it has to pass by this wn power of k. Okay, because it is the odd entry, so you have to multiply it. Then after that, it merge here, so it will be plus together. All right, so it be add together, and you get this value capital A as your xk lah. This is the first xk 0, right? So this is how it works for the top part. I'll explain to you why so later, but you just let's just understand this diagram first, okay? And then here, uh, the second xn, still the same xn now, so it will need to go through the bottom part, okay? And this one goes straight, okay? So b multiply wn power of r, and then you have a minus 1 here lah, so there's a negative. So you merge together, then you add, meaning that a minus wn multiplied by b, right? So because b passed by this, with this structure, you got uh, the xk, right? So this xn, you can convert it to xk. All right. So why this process? I can for now you cannot see how this process is related to uh, the uh, this these equations. Okay. So how is that possible? This equation can be translated into a butterfly structure. Okay. So first of all, the butterfly structure has n equals to 2, right? Because you see there's two value, right? So if n equals to 2, okay, uh, n equals to 2, okay, so n equals to 2. So here you would get summation of m equals 0 until 1. Okay, because 2 divided by 2 minus 1 equals 0. Okay, so sorry, this becomes because of 0. Right. So if n equals to 2, okay, so you need to find the 2-point DFT. Okay, so this summation will become summation of m equals 0, 2 divided by 2 minus 1, then until 0. Okay, so the summation limit is from 0 to 0, meaning that you only have one item. Okay, so you have f1 0 w n over 2, which is uh, w1, right? So n over 2, n is 2, so w1, and then m is 0. Okay, so you have 0 here. Okay, plus w2 power of k f2 m is 0. Okay, this one is similar now. If you replace n equal to 2 here, okay, then w 1 power 0. Okay, right. So this is your xk. Okay, so you can take away this now. All right, so you have f1 0. So in short, you have xk equals to f1 0 w1 to power 0, which is actually it give you a value of power 0, right? So give you a value of 1. Then this one also give you a value of 1. So in fact, this one you also can take away, right? So see, okay, so I decided to take this away. No need to write anymore because power of 0 get 1s. Pointer, okay, plus w2 k multiply f2 0 lah. All right. Okay, let me see. All right. Okay, so this is the even sequence. This is the odd sequence, right? Okay. So the odd sequence always need to multiply with this w. Okay, so then we can iterate the k. So x0 is f1 0 plus, if k equals 0, so this is power of 0, then it is 1. Okay, so if k equals to 1, then you get f1 0 plus, this is w2 to power of 1 is actually minus 1. Okay, 2 0. Okay, so this one you go and figure out why this is minus 1. Okay, and then this is 1. All right, so you can look at it from the complex plane, or you can expand this wn equals to ej 2 pi over n minus. Okay, so if you power of 1, then you see what is the value of this lah. Okay, so it is minus 1. So you see it is the sequence plus another sequence, then you got your x0 for n equal to 2, for n equal to 2, for 2-point DFT. Okay, and then for k equals to 1, okay, then you have f1 0 plus a negative 1 multiply f2, right? So it is just a plus and minus, right? So if you take out this, you actually have plus and minus. So essentially there is a multiplication of minus 1 here only lah. Okay, right. So if you translate this into butterfly, okay, then you can you can get the structure like this lah, right? So this one goes straight, okay, a, okay, and then the second one, this is a, it's like f1m lah. So this is like f2m lah. So this one has to multiply uh w, okay, then add together, you got this. So it is a one positive, the other one is negative, right? So this is the basic structure for n equals to 2, okay, right? Basic structure for n equals to 2, okay, right? So then, and then let's say n equals to 8 now. So if n equals to 8, okay, you can break it down into 3 stages because if n can be written as 2 to the power of v, okay, meaning that it can be written as 2 to the power of 8, okay, and sorry, 2 to the power of 3, okay, and the slide here says, okay, the total number of complex multiplication is reduced to 12, right? So if you put a sample, the numbers, let's say n equals to 8 lah, then if you calculate this, you get 12, all right? So the number of multiplication becomes 12, which is very low, okay? So how does it can be become 12? Okay, so you see here. Uh, so how do we break down this uh, FFT into three parts now, into three stages? Okay, remember that if n equals to 8, n equals to 8, then you can break it down into uh, a 4-point DFT. Okay, then you can break it down into a 2-point DFT. Then you still can break it down into a 1-point DFT. So there is three stages here. So therefore, you see here stage 1, stage 2, stage 3. There are three stages of um, breaking down. Okay, and then after you break it into the smallest uh, EFT size, then you can perform this butterfly structure to get the values here, right? Okay, and then you can do this to get the values here. Then with these four values, then you can continue to get uh, 1, 2, 3, 4, 5, 6, 7, 8. These 8 values, when you will go through a bigger uh, butterfly structure to get your x1, x2, x0 until x7. Okay, so that's the process here from left to right. Okay, from xn, you will go through stage 1, stage 2, stage 3 to get your xk. All right, so there is 3 stages. Uh, Actually, these processes can be done through these equations. Okay, just that they convert it into graphical methods. Okay, so there is choices for you lah. See, whether you wanted to apply these equations. Keep so up. So how do you do this equation? Is um, how do you use this equation? Okay, so you have to first start off with this. Get the n over 2 DFT equations ready. Okay, so this is another n over 2 DFT equations. Then create another 2. So there you have 1, 2, 3, 4, right? Then you have 4 terms here lah. If you continue to break it down, right? Continue to break it down. Okay, then another breakdown again. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, right? So if you still need to break it down, then you have to have doing this, you have a lot of terms equals to 1xk. All right, so you have many terms. If you use the equations to perform the FFT, also can, just that you have a lot of terms to calculate, which is very easy. So all the terms, if you got it, it's very easy to be implemented in computers. But for hand calculations, so you find that it is a lot of repetition. So these processes has been converted into um, a butterfly structure. Okay? Right. So later on, I would explain to you how to build this butterfly structure. But I wanted you to take note of this first. Okay, so this stage 1, stage 2, stage 3, xn is written here, xk is written here, okay? And you found that this is even odd, therefore you have w associated to the odd entry one. Okay, so you see here, okay, they are all following the odd uh, odd entry. And then you will see here also got, okay, so meaning that this is the odd entry, this is the even entry for this stage, right? So, and then if you also see here, there's a W multiplier. Okay, so you found that, okay, so all these 4 is the odd entry, all these 4 is the even entry. Okay, so you will see that starting from 4, then they become 2, then they become 1, right? So this is the butterfly structure that we are going to build. Okay, so it has these characteristics. Okay, so if you look at here, why is that the if n equals to 8, you got 12 complex multiplications, right? So you see, one butterfly structure, it takes one multiplications, right? So one multiplication. Okay. So how many butterfly structure here? So there is one, two. So because whenever you see this, then you know that you have to do complex multiplications lah. Okay. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that you have 12 complex multiplications, and the rest is complex addition. Okay, so you have 12 complex multiplication here, right? Okay, so therefore it is 12 now. So the total number of complex addition is 8 log 28, which is 34. All right, so this one you can calculate also lah. But the complex additions multiplications is the one that taking up most of the resources lah. So imagine you have a plus jb multiply with c plus jd. So the complex multiplication process is a lot lah. Okay, including the additions. Then you got c d e f, e plus f j f, for example. So to get this, you involve a lot of steps. So the complex multiplication is the uh, comparatively more complex than complex addition. Therefore, we can take these complex multiplications computation steps, take it as the a very important slowing down factor for the computer to compute now. Right. So once we understand roughly what is ahead, so let's see how do we build it. Right. Okay. So this is the comparison of computational complexity of the direct computations, meaning that you use DFT as use the DFT equations to calculate the XK as it is, okay, and versus the one with FFT algorithm, meaning that you break it down into a smaller part, okay, using decimation in time, okay. Decimations means you break down it in the time domain. So therefore it is called decimation in time. Okay, right. Um, so this N2, number of point. Okay, let's look at the one that we familiar, 8. Okay, so the complex multiplication in direct computations, okay, is 64. All right, but in FFT algorithm, okay, is 12. Right, so the speed improvement is 5.3. Yeah, it's 5 times more faster than the conventional DFT equations. Right, so and then these are the rest of the number of computations. You see this DFT, direct computations, you see it grows very fast. For 1,000 point of DFT, it needs 1 million steps, right? But for FFT, it needs 5,000 steps, and the improvement factor is 200. Yeah, so therefore, in any software or hardware, in oscilloscope, probably you will see that some oscilloscope they offer the option of FFT. This is the algorithm that everyone prefer to use rather than this original DFT equations and direct computations. Of course, if the number is low and you have plenty of abundant of computational resources, okay, then probably you don't mind to code this into your program. Okay, but if the n is large, then you have to use FFT, right? So that is the idea here. Okay, right. So the things is, how do we construct this, right? Okay, this one is the last. After that, then we'll finish now. Okay, so I need okay, I will need canvas. Okay. Today we have only 10 participants, including myself. Okay. Uh, all right. But anyway, the session is recorded. Okay. So I hope those who are not here, um, please view this recording. If not, um, you cannot follow later on. Okay. The discussion later. Okay. All right. So first of all, if you wanted to construct the DFT, do I have the um, example? No example, but okay. All right. So the first step, okay, is to write down the column vector for xk, right? Okay. So you write down the column vector for xk. Okay. List xk, right? So let me write it here. So this is xk. All right, so this is the answer that you want to find. Okay, let's say you are given xn equals to 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's take an example of n equals to 8. Because we wanted to uh, build this, right? So this is 8 point. Okay, so this 8 point DFT, right? Okay, so let's say n equals to 8. Okay, so I will start it off with sk column vector. Okay, I need this answer. Okay, I need to find this. Okay, I'm given this. This is given. Okay, and then the question says n equals to 8. Please use FFT to find sk. All right. So the first step is okay. So I will list down the xk. Right. Um, so okay, x0, x1, x2, x3, x4. Okay, x5, x6, x7. Okay, so there are 8 of them, right? Okay, so I list it down here. Okay, according to these equations, where's the equation? This one. Okay. Okay, according to these equations, xk can be broken down into f1k and f2k with a multiplication of wnk lah. This here, right? You can see, right? So I write down here. Okay, according to the theory, okay, we can xk can be written into f1k plus wn k f2k, right? So I'm going to break it down, okay, in this f and f2 lah, okay, right? So okay, so here I would write here fk lah, right? So I write here fk. Okay, right? So this is my f10, f11, f12, f13. Okay, I stop at 3 because uh, it is half the length of the xk lah, right? So remember, f is actually half the length of the x. And then I have my f2. This is my even entry, right? So this is my odd entry. f20, f21, f2 2, and f23, right? Okay, so this is my f23, right? So this is my odd entry. Okay, I do not know what is F yet, okay, but I know that the relationship between F and X is defined by this equation, right? So, for example, okay, if K equals 0, so it would be X0 can be calculated from F10 plus W8 K to the power of 0 F20, right? I know that if I want to find X0, uh, I can use F10 and F20 to calculate X0, right? But this F20 have to multiply with W8 to the power of 0. Okay, so I will construct my first connection. Okay, okay, I construct my first connection. So F1 is to calculate X0, okay, I need F10 and I need F20, right? Add them together. But of course, F20 have to go through a W80, okay? Then I can calculate my X0, right? Similarly, okay, if I wanted to calculate my X1, then I need F1 and F2, F11 and F21 to get my X1. So if I continue this process, you see that I can actually draw this, okay? I want to calculate my X40, I can use my F10 and F20, but for F20, it has to go through with W84 lah, right? So if I continue this process, I'll be able to draw the um, all the connection lah, right? So let me just quickly draw all the connection. I only show you how to get X0 lah, but the rest you can infer it yourself, okay? Right. Okay, so to draw it nicely lah, okay, okay. So this like this, okay, and then I can draw this, okay. Then I can draw this, then I can draw this. Okay, so this is my first stage. All right, and then I know that the one that coming out from the odd entry, it has to multiply with a W, right? Okay, so this one, this one, this one, this one. Okay, so I would need to give them uh, the W lah. Right, so this is the first one is W8 power of 0. Okay, you cannot see. The first one is W8 power of 0. Okay, the second one is W8 power of 0, right? So I use red color. Okay, this is W8 power of 0, and then this is W8 power of 1, W8 power of 2, W8 power of 3, W8 power of 4, W8 power of 5, W8 power of 6, and W8 power of 7, right? So go from 0 to 7. I follow this equation. Okay, I follow these equations, right? So then if you continue to increase x1, right, can be found from f11 plus w81, right? Because we follow the k lah. Okay, f21. Okay, so if you continue to iterate the k, then you can write all this equation out. Then it is very um, natural for you to draw this structure. Okay, right. So let's say to find x0, right? Okay, so there's several ways to draw the butterfly structure lah. Okay, so this is F10 and F20, right? Okay, then here is W80. Okay, right. Some uh some structure you can write this like this. Okay, uh, it depends on your preference now. You can write it this way. It's the same. Okay, Okay, so this is F10, F20, and then write it here, right? So this is W80, then you get your X0, right? So you, instead of writing it here, you can actually move it further. You can just put it here lah. So because you know it has to be multiplied with a factor y, right? So only then you add, right? So you can draw this, okay, or you can draw like this. Is all right. Okay. Anyway, it will just pass by this one. So this is the textbook butterfly structure. Okay. So this is the style that I use lah. All right. I put it near to x0, but the textbook put it near to f2, right? So it is both can be used, right? So if you look at uh, the structure here, okay, so it actually move it near to the input lah. Yeah, but it is all right that if you want to move it near to the output is also okay, no problem. But for my style, I put it near to the output lah. Okay, so I'll stick to that. But please be remember that there's just the different style of writing. Okay, different style of writing. It's all right one. Okay, so then you will see that my butterfly structure is a little bit from different from the textbook lah, because I put it near to the output. You see, it's here, right? So I do it like this. No? Okay, so this is my first stage, right? So this is my first stage. All right, remember that there is a pre-stage. Okay, so we need to build it um, uh, this lah, huh? I have to build it one by one, huh? Okay, all right. Okay, all right. So next step, huh? Okay, so we know that now um, this is the structure that we, you know, the equations that we can get, the butterfly structure that we can draw from the equations. Okay, okay, almost 1 hour already. Okay, right. So actually, how to get our F10, F11? What is the values that you know, to get this F1 and F2? Uh, in fact, uh, F1 and F2 is gotten by a DFT 4-point DFT direct computations. Okay, direct computations. Okay, so if I draw it correctly, it should be like this. Okay, so there's a DFT. Okay, it's 4-point. Okay, if you direct computation, this is direct DFT computations, direct, right? And it is 4-point DFT lah. Okay, so the input to this direct computation equations to get F10, F11, F2, F12, and F23, according to the theory, is F1M. Okay, the theory says use F1M. Okay, so what is F1M? F1M is X bracket 2M, is the even entry of the Xn, right? It's the even entry of the Xn. For F2, it is X2M plus 1. It is the odd entry of the Xn. Okay, so that means in order to get my F1, here I need to do a direct computation, direct computations of X0, X2, X4, and X6 in order to get my F1. Okay, so similarly, okay, to get my F2, I still need to do a direct computation of 4-point DFT, and then here would be my X1, X3, X5, and X7. Okay, do a direct computations using DFT equations to get my F2. Then from my F2, then I can calculate my XK lah. This is according to the theory lah. Okay, And then I know that I can further break down this into odd and even. Okay, so I can because this is 4 point DFT, I want to break it down into a 2 point DFT lah. So that's my goal lah. All right. So in order to break it down, okay, in order to break it down into uh, from 4 point DFT to 2 point DFT, uh, this would be my even, and this is my odd, right? This is my odd entry already. 4 and 6 is my odd entry. 0 and 2 is my even entry. Okay. So I wanted to break it further lah. Okay, so I don't show you here. Okay, I just show you this part. Then you sendiri infer the bottom lah. Okay, so now let's say now I want to padam this lah. Okay, padam this because now I want to focus on how do I get my F10 and F11. Okay, through another smaller DFT lah. Okay, so I'll take this out again. Okay, I'll take this out. Right. Okay. 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 Right. The upper half. Huh? So let's say we call it G. Okay. So I have G1, 0, G1, 1, then G2, 0, and G2, G1, 0, 0, G2, 1. Okay. And then here is my connection. Okay. Here's another connection. Okay. And I know the odd entry, it will be connected to have to multiply with W4, right? W4, 2, and W4, 1, 2, 3, 1, 0, 1, 2, 3. Okay, right. So, all right. So then I need to rearrange my, I have to rearrange my X already. Okay, because I need to group them even, uh, the even entry, this even entry will produce these two, and the odd entry will produce these two, right? So I have to rearrange the X0 already. So I'll write it here. X0 and X4 is my even entry, and X2 and my 0, 2, 4, 6, right? And X6, 0, 4, 2, 6. Okay, so it's my odd entry. All right, so they will go through a 2 point DFT. All right, so it will be like this: 2 point DFT, direct computation to get this, then another direct computation, 2 point DFT to get this, right? Okay, so I will do the same for the bottom lah. Okay, so X1 and X5 is the even entry. Then X1, X5, X3, and X7. Okay, right. So I will take this out. Okay. So this G, right? So I use G3 lah. G3, G4, G4, right? So sorry for the bad sketching. Okay, right. So and then you have 1, 2, 3, 4. Then the W4 you repeat W4 0, W4 1, W4 2, W4 3, right? 0 1 2 3, right? So uh, then the yeah, this one, right? So come in and come up. Okay, right. So so let's check the answer. Right, let's check the answer. What to check? Okay, you see here my my xn equations, right, is now 04261537, right? So are we close to that already? Okay, if you look at here, okay, 04261537, right? So is we are almost there, and we have done stage 3 and stage 2 connection. All right, we have done stage 3 and stage 2 connection, right? So if you see here, this W80, W82, this is actually W4 lah, right? W4. So if you see that is slightly different from what I sketched, but if you move them back to the line up here, right? So you found that it is uh, how to say, you still get the answers lah. Just that uh, there's uh, the other way of sketching the butterfly structure. They move this near to the input. All right. So and then they make use of this negative -1 um, this what do you call, symmetricity properties, okay, according to this equation. So they are actually using this equation here. But I prefer I prefer these methods, okay, because it is less prone to error lah. So uh, the idea is let's try not to make mistakes lah. So sometimes there is, you have to remember the odd entry, you have to associate it, you have to give it a -1 here, right? So that's very dangerous to do mistakes. So why not we just follow these equations to do the work, right? So this definitely would not be wrong. Okay, so therefore you see me have this value here. Okay, right. So this +1, okay, this -1, right? Okay, right. And then they are using W8 lah. So I'm using W4 here, but W8 and W4 is interchangeable by the power lah. Okay, so it's up to you. Okay, so do you want to simplify it to make it like the textbook, or you can use these methods? Is also all right. Okay, both are acceptable lah. Okay, as long as the answer is you can get. All right, so now you have a 2-point DFT, right? So these are the 2-point DFT process. And you think that, okay, so I still want to break it down to another smaller DFT, which is 1-point DFT. Okay, so if you want to break it down into 1-point DFT, this is your even entry, and this is your odd entry, right? So you can directly do a butterfly structure on uh, these two process already. Okay, so let me do the first one. Okay, so this DFT, I can take it out. Okay, right. So the even and odd is already set. Okay, so to calculate G, right? So I will draw this, right? Okay, and then this is my W20 connected to the odd entry, and for the second point, also connected to the odd entry, this is W21. Okay, and this is my X and list. Okay, I can continue to do the same for the rest, right? Okay, I can continue to do the same for the rest. Okay, right, like this. Okay, then I W20 W W21. Actually, W2 to power of 0 and W2 to 1 is positive 1 and minus 1. Okay. In fact, if you don't write this W2 0 and W21 is all right because multiply by 1, why you need to write it, right? So, but this is for simplicity lah. W2 0 and W21. Okay. Last one. Okay. Where is it? W2 0 and W21. Okay. So then there you go. This is your entire, oops, this is your entire butterfly structure done. For n equals to 8, you have stage 1, stage 2, and stage 3. Okay. Then your butterfly structure, oops, your butterfly structure is, just take note. So there are 4 butterfly structure here. You see, this is 1, right? 2, uh, hard to see, but there are 4 butterfly structure here in this stage. And then this stage also got 4. 1, 2, 3, 4, right? And then here also got 4. 1, 2, 3, 4. So there are total of 12 butterfly structure altogether, 3 stages for n equals to 8. Okay, so this is the, how to say, this is the entire process um, to get the answer from xn to xk by hand, okay, by hand, using FF2 destination in time radix 2 algorithm. Okay, so you might think, oh, this is very complex, right? So can I use uh, a memorizing method? Okay, particularly, how do I know in the end I will get x0, x4, 2, 6, 1, 5, 3, 7, right? So how do I arrange this part, right? Uh, so there's a method to get this arrangement of xn very quickly lah. Okay, we call it bit reversal method. Okay, so how do we quickly arrange this Sn, right? Okay, how do I know the sequence? How do I know it should start from 0, then the next one is 4, and the third one is 2, 6. How do I know? Okay, so it is like this lah. Okay, Xn. You start off with arranging the Xn in normal order first. Okay, so x0, x1, x2, x3, x4, x5, 6, and 7, the last one. Okay. Next is you find the binary representation of this index, right? So the binary bit. Okay, the binary is so since n equals to 8, right? Okay, so the binary number there would be 3-bit lah. Okay, so 3-bit binary representation of the index, right? So it is 0, 0, 0 for the first x. Okay, then this is 0, 0, 1, 0, 0, 2, 0, 0, 3. Oh, sorry, cannot be 0, 0, 2, 3. It should be 0, 1, 0, right? What am I doing here? Okay, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. Okay, then you reverse it, right? You do a reversal, right? So reverse it. Okay, so just fold it lah. Right, so this one fold it, this one fold it, stay the same. This one fold, this one fold, this one fold, this one fold, this one fold. Okay, then you convert it back to the decimal representation. then you see that it is 0. This is 4. This is 2. This is 6. This is 1, 3, 5. Is it? 1. This is 1, 5. This is 5, right? This is 0, 4. This is 3. This is 7. This is 5, right? 1 plus 4, right? Yeah. So you see that it is 0, 4, 2, 6, 1, 5, 3, 7, which is similar to the arrangement here, right? Okay, so which is similar to the arrangement here. So this is also 0, 4, 2, 6, 1, 5, 3, 7. Okay, uh, so this is the way that you can quickly list down your XN. Okay, so I give you a quick summary. Okay, it's already 9:40, 10 minutes past. We should doing the tutorial already lah. Okay, so first of all, if you are given n equals to 8, okay, and you are given the xn, okay, you are given the xn, there is 8 element here, right? You are given, and you are requested to find xk. So for the first step, what you need to do is you write down your xk uh, column first from 0 until 7. Okay, the sequence is normal. Okay, and then because n equals to 8, you know that you would have 3 stages. Okay, so you have 3 stages, then you need to build this lah. Yeah, stage 1, stage 2, stage 3. So you quickly draw the butterfly connection for stage 3, 2, and 1. Okay, so how do you draw the first from starting this stage? You separate it into half first. Okay, 4 at the top, 4 at the bottom for n equals to 8 lah. Okay, depending if n equals to 16, then you separate it um, this the number of values, the number of variable here is 16, right? So you have to have 8 at the top, 8 at the bottom, and you separate it. Then you need to connect the odd and even, okay, using the butterfly structure. Okay. Then after that, you for the second stage, then from 4, you half it into 2, right? So like this, right? So 2. Then after that, finally, you half it into uh, smallest value. Then you draw the uh, connection. Okay. Uh, for the arrangement of xn, then you use bit reversal method. Okay. For n equals to 8, if you do the bit reversal method, then you have 0, 4, 2, 6, 1, 5, 3, 7. But n equals to 16 or n equals to other 64 or n equals to 4, right? So the bit reversal method still applies. Okay. Uh, you still do the bit reversal method, and then you write down rearrange the xn into that this part here lah. Okay, it wouldn't be wrong one. Okay, the bit reversal method is wouldn't be wrong. Okay, so that's the process, and you can see that this method is very efficient because first, to do a bit reversal method for xn in a computer is pretty quick lah. Okay, because you just need to fold it, then you can directly get the this sorted out very quick, and it save memory. Okay, because from x0 from xn to gk, from xn to gk, after you do the calculations, this value you can wipe out already. This value you can wipe out from the memory already. Okay, then you have g1 and g2, g3, g4. And from this stage to this stage, then you can replace the memory can be replaced by the new value of f already. So in the memory this management, the computer is very efficient, okay, and also the process is also quick because the number of multiplication is only 12 for n equals to 8. Okay, so therefore, okay, almost all the kind of processor out there, they do FFT this way. Okay, right. All right. So okay, so that is the Okay, let me see. Okay, so that is the methods how to uh, draw this lah. Okay, draw this butterfly. Okay, and also one more point to highlight now is uh, why does that this method is called why this is called decimation in time lah. Okay, because the rearrangement of the butterfly structure is on the time domain, right? It's in the time domain here, right? So this is the decimation in time. Okay. There's another way now. There is decimation in frequency, but it's not shown here because the process is almost the same. So if you know decimation in time, fast Fourier transforms, then decimation in frequency is the same process. Okay, just that the arrangement of xk is bit reversal. Okay, right. So the next things to oops. Okay, so the next things to notice is here. All right. So this is memory address, right? So this bit reversal method. Sorry, I wanted to get the pen. Right. Okay. So from here to here, right? So this natural order, okay, is from 0 to 7. Then uh, decimation number 2. Okay, so this is the even number, right? This is the even number, right? So you got 0, 2, 4, 6. Okay, that's the even number. Then this is the odd number. Right, then you further uh, group them again, okay, for another stage. So you have this and this as your even number. Okay, so this is your odd number, this is the even, this is the odd, right? So this is the exactly the process that I've shown you in the when I sketched the butterfly structure. Okay. So if you look at here, how to get the 0, 4, 2, 6, 1, 5, 3, 7, you can use the bit reversal method. So this is the natural order bit binary bit from here. Okay. Then you reverse it, right? You reverse it, then you write down the decimal point, then you will get 0, 4, 2, 6, 1, 5, 3, 7 from here, right? Okay, right, bit reversal. Right, the data is stored in the bit reversal order. Okay, right. So that's all for chapter 2.2. Okay, I hope you are still there. Okay, no questions asked in the chat box. I assume you are all right lah. Okay. Okay. Maybe let me see. Maybe we do a few questions of tutorial real quick lah. Because I've been long time didn't solve the tutorial equations. Let me see what is the which tutorial we are at right now. Is it tutorial 3 or 2? Can't remember. Okay, let me give me one moment to check. Is anyone remember we are now at which tutorial questions? Is it 2 or 3? I think we have done question 2 or tutorial 2. I think tutorial 2, question 3 and 4, we haven't done it yet, right? Okay. So we'll do that 2 question. All right, so I can, so there's not many students here lah. Um, I also worried that those who are not attending those who are not attending the lecture and tutorial, if they do not follow the my lecture and tutorial and then come next week to attend my lecture, then they will lose. Okay, because many things are interconnected one. Okay. Okay. Yeah. Brian said 3 and 4 haven't do. Okay, so we quickly do 3 and 4 uh, today lah. Okay, Saturday. Then tutorial 3, then we do it another time lah. Because if too many questions we discuss, then I'm afraid some of your classmates cannot follow. Then they will be very suffer during the final exam. Okay. Okay, so tutorial number 3, determine the range of values of the parameter for which the linear time invariant system, okay, linear time invariant system, it is an LTI system, meaning that superpositions and process is linear and it doesn't depend on time. Okay, with the impulse response is stable. Okay, so let's I use I use this canvas to do the question now. I'll put it right here. Right. Tutorial 2, question 3. Okay. I move this to the other screen first so that I can tutorial 2 tak ada, right? Tutorial 2. Okay. Yeah, move this away. Okay, so tutorial 3 says, okay, so determine the range. So they want a range of values uh, for A. So that, okay, so that find the range so that Hn is stable. Okay, so what do you mean by a stable system? Okay, and Hn is LTI lah. It's also mentioned that the system is stable is when when it is given an input, it doesn't grow to infinity. Okay, so it is bounded lah. Okay, if you still remember Bible, okay, which is forgot where is it? Let me find it. Okay, chapter 1.1, 1.2, I forgot. Should be 1.2 lah. Okay, I just want to refresh your memory a bit. So that whenever you find problem, then you can uh, always know where to get it. Okay, just find stable. Okay, so stable and unstable system. Okay, if the system is stable or bibo, okay, if the bounded input produce a bounded output, okay, so that's the definitions, meaning that the input and output cannot be infinity lah. Okay, so when we know this, then we have this let's look at this. Hn is an impulse response, right? Impulse response. Okay, right. So impulse response means, okay, it is a system here that is, this is an LTI system. Okay, you will get your impulse response if you insert the impulse, right? So therefore you get your Hn, right? So so that's what it means. So this is already bounded. Okay, so we want to know Hn. This system itself, okay, is it a stable system? Okay, so meaning that if we insert some values to it, whatever input, bounded input, this Hn has to be stays uh, bounded lah, cannot grow to infinity lah. Okay, so let's look at the equations of Hn. It is given to us. Okay, the equation for Hn is this one. I keep it first. I copy it here. Okay, I'm having the other screen now. Didn't show you, but I write down the equation here. a power of n for n greater than 0, and even, then you should use these equations, 0 otherwise. Okay, so this system is quite uh, convenient because it says that if you are having an Hn, okay, you need to care about the n that is at the right side after the 0, okay, because for n greater than 0, then you should use this equation. So for the values here, Hn equals to a to the power of n, okay, because it says like this, and it even restricted it to the even entry, right? 2, 4, 6, and so on. So how about the odd entry? They are 0, right? So all these even entry is odd entry, they stay at 0. Only those um, even numbers n, they have some value according to this, depending on what is a lah. Yeah, depending on what is a lah. Maybe it's 5, 10, don't know. So it will have different values. Uh, 0 otherwise. Okay, so all here is 0 lah. Okay, so we need to care about the uh, positive n side of the uh, Hn. Okay, see whether those can grow to infinity or not. Okay, right. Okay, so in order to, oops, I should keep it now, but sorry about that. But we understand now, so how this Hn looks like. Um, if you normally, I would like to put it into graphical sketch, then I will see, I will be more understand, right? Okay, so in order to, let me see, to study whether it is, let me see, there's the equations is here. Okay, give me a moment. Particular two. Accelerator. Okay. Yeah. Just one moment. I forgot the equation. Okay. All right. Okay. So for there's an equation now for Hn to be stable. All right. It has to. We have to ensure that the summation of Hn from n starting from minus infinity to infinity, Hn modulus is not is less than infinity lah. Okay, it is not arrived at infinity. So if we sum all the Hn amplitude, okay, amplitude of it, if it is for all the range lah, because we can see that this Hn actually is according to this equation it is an infinite sequence, right? So one way, if there is one element that is infinity, then it is not, it is already unstable lah. Okay, so in order to consider all the values, okay, they are finite, so we can assume that if all the elements added up together, it is not infinity, then the system sure will be stable one. Okay, so we need to check whether the summation of all these Hn modulus, okay, their amplitude lah. Okay, so we only look at the amplitude, not the sign. Okay, if they are smaller than infinity, then for sure this Hn would be uh, infinite. So this is the equation that we wanted to prove. Okay, whether Hn is bounded or not. Okay, so we'll check this one. Okay, right. All right. So to do that, Okay, so we write the equations. I will write here 0, okay, because I know the negative infinity, that part, there's all 0, no need to sum lah, and also even. Okay, I would only consider the n at 0 and even until infinity, okay, for this hn, right? And I want to see why this, okay, right? I want to calculate that. Um, hn is a to the power of n for this uh, position and at 0, starting from 0 and even, okay, then I can write it here, and is 0 and even, okay, a to the power of n, like this, okay, right? So I can factor out the n, right? Or I don't need to factor out, also can now, so I'll just leave it there. uh, I can, because normally it will be easier if I iterate the n from for a normal sequence lah, like natural sequence, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I wanted to uh, modify a little bit this range. I want to include the odd numbers. Okay, so here I'll put 2n. Okay, so by including the 2 here, I will ensure that the power of the a is always an even number. Okay, right? So these two essentially is the same. Okay, every even number uh, here will be, I will ensure here to be when n running from 0 until infinity lah. Okay, so it will be 2, 4, 6, and so on, including 0. All right, so this is also going 2, 4, 6, right, and so on. Right, so essentially this 2 is the same. Okay, I add a 2 here lah. Then I take away the even words, okay, from the equations. Okay, right. So okay, so the question is, what is the value of a so that the uh, these summations, it doesn't grow to infinity, right? So let me give you okay, so this 2n, I think we can put it outside lah. Can we? Yeah, yeah, no need lah. So just put it inside. Okay, right. So we have the geometric series equations. Okay, so let's say you have um, a summation of power series, right? So let's say you have 1 plus x, or maybe not 1 now, I use x to the power of 0. Okay, x to the power of 0 plus x to the power of 1 plus x to the power of 2 plus x to the power of 3 plus, and so on. Okay, until infinity lah. Okay, until infinity, never stops. We can write these equations into a summation uh, short form lah. Okay, summation sign. Okay, uh, we can write it into 1 divided by 1 minus x if the x is smaller than, if the x, the amplitude of x is smaller than 1. Okay, meaning that if this x here, okay, is the amplitude is not greater than 1, meaning that maybe it is 0 0.5, 0 0.2, 0 0.8, it is not 1, okay, or minus 1, okay, then we can write it into compact form, right? So converge value, it will converge, right? If the values is smaller than 1. But this one also makes sense, like you see, if x is 0 0.2, right? So you have the 0 0.2 power of 0, then 0 0.2 power of 1, add together, then 0 0.2 power of 2 plus 0 0.2 power of 3, right? So as the power increases, you will find that the values at the back here is very, very small, okay, as the power increase, okay? Until one point, it is very insignificant, okay? Too small to be included into the values. So it will approaching this value as it grows to infinity. So there is equations like this. Okay, so in order for uh, this Hn to be uh, stable, so it has to be sum to this form. Okay, it cannot grow to infinity. So um, so here we could say that if, okay, um, okay, so too small. Okay, so I rewrite the equations here. Okay, so Hn summation n equals to 0 even Hn, okay, equals to this a to the power of 2 uh, right? So n lah, we put the n outside here lah. Okay, so this is like our x lah, right? So this is like our x. Okay, so in order for this to be converged into one number, it doesn't go to infinity. It's only when the a power of 2 is smaller than 1, right? So for Hn to be stable, so this must be smaller than 1. Okay, so that uh, summation of Hn is equals to 1 minus a to the power of square, right? So it will be stable, okay, for a that is smaller than 1, and it will converge to this value. And the question actually asks, what is the range? Okay, what is the range, right? Here, what is the range of value of a? Okay, the range, they want the range. Okay, so the range given here is a to the power square must be smaller than 1. Okay, so this is the range of the a of the value, right? So so you might ask, do we need to square root both sides? I think, yeah, you can do that. Okay, as long as this is more than 1, then there's if you square both sides, then you will still get this lah, right? So you would so this is the range lah. Okay, but if you are stop right here, it's already got the answer lah. Okay, so the range of a for the system to be stable is this range, and with this range, we will ensure that the summation of Hn absolute would stays to this value. They will converge to this value, right? A closed form solution, right? So this is the answer for question 3. Okay, right. Uh, Let me see so far. Do you have any questions? Okay, this is a chat box. Huh? All right. Okay. So next is question number 4. Right. Let's look at question number 4. Okay, I hope you have done question 2C. This one, because I didn't give you the solution, I only give you the answer. Okay, so please verify that whether you got the answer correct lah. Okay, so this one you can double check the answer, your answer and my answer. Okay, so if there is something that is you cannot get, then you can inform. You can check with me lah. Why is that your answer is not the same with mine lah. Okay, right. So question 4, we solve this last question lah. Determine the autocorrelation sequences of the following signal. What is your conclusion? Okay, so this one is actually meant for REE student only and RTE student. RMH student doesn't need to do autocorrelation. Okay, so this topic is not in uh, the syllabus of RMH. Okay, right. So let's do this. Okay, so question number 4. Okay. Um, so xn equals to 1, 2, 1, 1. Okay. So you have four values here, and you are asked to look for the autocorrelation. Okay, autocorrelations means you sendiri correlate with sendiri lah. So xn correlate with xn. Okay, so that is this is what it means, autocorrelation. If it is only correlations, then there will be xn and yn, two different sequence to perform the correlations equations lah. So let's look at the equations of autocorrelation. So if you check the uh, lecture notes, okay, you will see this xx, meaning that x is correlate with x. Okay, so you have two xx here is equals to summation of from all the possible n value, xn and xn minus l. Okay, you see that these autocorrelations is very similar to um, it's very similar to convolution sum. Okay, just that the second terms here, which is moving, the moving sliding x when the n is changing. Okay, so there's two variable here, n and also l. Okay, so it doesn't, it's not folded, right? It's not folded. Okay, right. So we'll do one by one. Okay, so let's look for uh, L equals to 3. Okay, so Rxx 3 equals to summation. Okay, so n it is from 0 to 3 lah. So if you look at this, okay, so assuming this is 0 lah. So from 0 to 3, xn xn minus l. L is now 3. Okay, so we have set it to 3. Okay, so you need to iterate the n from 0 to 3 lah. X0, x minus 3, okay, and so on. Of course, x minus 3, if n is 0, x minus 3, there's no value lah. Okay, so yeah, this is multiplication of 0. Okay, so if you write down all the equation up here, you will get this. Write down the equation here. X0, this is when we iterate for n equals to 0, x minus 3 plus, this is when n equals to 0. Okay, x1, x minus 2 plus, this is when n equals to 1. So I'm iterating uh, the n, okay, after I fix the L, right? So x2 and x3, so I don't indicate the n anymore. So this minus 1, this is x0. Okay, then you will find that the answer is 1. Okay, right. So then you continue with all the L. Okay, so L3, so L equals to 2. So Rxx2, you get 3. And then Rxx1, you get 5. So this one, you can, I leave it for you to calculate yourself because just to save time now. Rxx0, you get 7. Rxx minus 1, you get 5. Okay. Uh, what else? When does it stop? Okay. So Rxx. So when should you stop, right? Is when all the uh, you're moving you're moving the windows of Rx, right? The xn, right? So until it arrives at 0 lah. So there's infinite 0 that come up, and you should stop right there lah, right? So Rxx minus 3. So we got 1. Okay, so if you continue r minus 4, then you get 0. R minus 5, you get 0. Okay, similarly, Rxx4, Rx5, you also get 0. So you ignore the 0 lah, because they already disengage from the overlapping. Okay, so you will get the answer of autocorrelations of Rxxl to be 1357531. Right, with this is the origin. Okay, 7 is the origin here. Okay, it's the origin. All right, so what is the implications that uh, from here? So what can we understand? So I mean, what is the what is so great about these numbers? What does that? So why do I need to do autocorrelation? And I get this bunch of number. What does it tells me? Okay. So you will see that there is one numbers that is very high in values, positive some more. Okay. It is located at RXX 0. Okay. It means that these numbers here is actually telling us uh, at this position, the signals are very similar. So high similarity. Okay. And this is when xn and xn, because we are doing correlation now, so we are comparing uh, xn to xn. So they are very similar when they are overlap. There is no time shift lah. The shift between x and x is 0. Okay, L equals 0 means according to the equations, there is no shifting lah. So you see, the equations is here. Okay, right. So minus L. If L is 0, then Xn multiply Xn. So that's the highest number, right? Okay. So this the numbers is the value is highest. So there's a high similarity at L equals 0. Okay. So from here we could say that they no, this is uh, the best similarity cases for this X lah. And you see that the similarity drops. Okay, when Xn is shifted away, right? They are shifted away. Okay, so these numbers actually telling us how similar these two sequence are, their patterns. Okay, and they pointed out to us what is the position that is highly similar, right? So this is what we can infer from these correlations value. Okay, so how does it can be applied to the radar application? So let's say you are doing correlations from a radar, right? So if there's a radar that it transmits a sequence out lah, xn lah, okay? Then after it hits some object, then it return yn, okay? So then you will do the correlations between xn and yn lah. Then you got a bunch of values, okay? Using different L lah, right? So then you found that in a particularly L equals to 10, the correlation is very high. So there's a very no, there's a very high similarity of sequence happening at L equals to 10. Yeah, so you know that there's a time delay of L equals to 10. So there's a 10 unit of time that's delay that the xn is returning back, right? So, but of course, this yn would not be exactly similar with xn because when it is emitted out, it go through the air, atmosphere, then they reflected back from the object in the sky, come back, then of course the attenuation is gone, then all the values is changed lah, and there may be some white noise. Okay, so then from here we know that, oh, okay, so we know what is the delta t, the object that in the sky and coming back. So then we can know, okay, so our signal should be this one, high similarity, okay, and it is delayed by 10. Okay, so then we can estimate the distance lah, of the object from the radar, right? So this is uh, the indications that we can get from the values of the autocorrelations or correlations coefficients here, right? So this is being the highest, and then when it is uh, how to say, when it is disaligned, then the similarity drops until 0, right? Okay, right. So that is question 3 and 4 for tutorial 2. Okay, so I think we are a little bit slow lah, but it's okay. If there's necessary, then we might want to have some extra class lah. Okay, but for today, I think we stop right here because we do not have many students attending this class. Uh, so we keep just minimal content for today, but still already 10:19. Spend some times also. Okay, I think we can stop right here. Uh, do you have any questions so far for the FFT and these two tutorial? Is it all right? If it's okay if you still are digesting what is happening in the lecture. You can always ask questions. Let's say you don't want to ask in the class, you can send a private message through Google Classroom to me, or remind me. Okay, I have a questions. I post that in the Google Classroom, but sir, you ever answer? You can remind me that. If you do not, if you do not prefer to speak up in the class lah, it's all right. Okay. You can send a message or email lah. Okay. Sometimes I might miss your email because every day I have too many email.